So what I want to do now is talk about sections 11.1 and 11.2. So 11.1 we'll start by talking about harmonic motion. There's not a whole lot I want to cover here. So you've got exercises 1, 3, and 5. And really we're just going to be talking about things like frequency and wheels. Talk a little bit about the bicycle type problems that we've covered in this class. Although I know we covered them in class, I don't know if I've put them in the YouTube series or not. But I'll just sort of mention those briefly. I would like for you to look at examples 1 and 3 in the book. So we often model something that is nearly periodic by what we call harmonic motion. That's the title of this chapter. So, I can't think of anything in this universe that is actually periodic. If you have like a sound wave, it looks pretty periodic for a while, but it has a start and an end, whatever. So these are sort of ideal models, but the number of cycles per second, well, cycles per unit time of and I'm just going to put nearly periodic phenomenon is called its frequency, which should make sense. It's how frequently something happens, so it's its frequency. We use hertz, and that's abbreviated HC, to count cycles per second. So, as a quick example, if a string vibrates at, let's say, 500 hertz for 3 seconds, how many cycles does it complete? Well, the answer is, we just convert. So 500 hertz is 500 cycles per second times 3 seconds. Seconds cancel, and we have 1500 cycles. All right, so that's the kind of question you might see. Another type of example, and I just want to sort of discuss this here, so it's for sure in the YouTube channel, because I don't remember, I know I did this in class, but I don't know if I did it on the YouTube channel, is I just want to talk a little bit about sort of the wheel type problems. So the wheel type problems are going to be things where you have, maybe a gear of, say, R1, and it has a fixed axle with some wheel, and this wheel has some radius, let's say R2, and this gear has a chain fixed to some other gear, which has a radius, say R3, then we oftentimes will talk about how the wheel turning, so that this big circle is going to be the wheel, how this wheel turning relates to this small gear turning. And basically the way this is going to work is this chain that connects these two gears is going to ensure that the arc length that this wheel rotates through is preserved, and this gear rotates through is going to be the same arc length that this gear rotates through. So we have S equals R theta for the arc length of a circle, which means that if this gear rotates through some number of rotations, or some measure of rotations using theta, then we would have, S equals, say, R3 theta 3, however much, this third gear, I guess gears and wheels, however much this third round thing rotates, is going to be the same arc length that the first one rotates through, so R1 theta 1. So if I know that this rotates through, say, 3 inches, then this rotates through 3 inches. But since this gear is smaller, 3 inches is going to be a lot more angle than this gear. So that will give us the ratio between the angles. Similarly, because this, oh goodness, I don't like it when it automatically zooms. This axle is fixed between this gear and this wheel. So similarly, we're going to have that theta 1 is going to equal theta 2 because they have a fixed axle. So we've already discussed this in class. We did what I called a bicycle problem a while back. And like I said, if you look at the examples in the book, that'll explain this a little bit more fully, but I just wanted you to see that sort of the key things are, by using s equals r theta, we have this relationship, which is just that the length of the chain is preserved, and this relationship, which is just saying that these two share an axle. Okay, so the next thing that I want to talk about in this video is section 11.2, and this is the law of sines. The law of sines is, I think, relatively straightforward. Your suggested exercises are 1, 3, 5, 7, 11, and 13. And so basically the key topics here are the law of sines and examples 1 and 2 in the book. So the law of sines, proving the law of sines might take a little bit of work, but the law of sines in and of itself is fairly simple. And it basically says, law of sines, it basically says, in a triangle with side lengths A, B, and C, and opposite angles measuring alpha, beta, and gamma, respectively, we have that sine alpha over A equals sine beta over B, which equals sine gamma over C. I'll just draw a picture here. We notice sort of the big thing about this is we're not assuming that any of these is a right angle. So this triangle need not be a right triangle. So that's kind of an interesting thing, is so far we've mostly been dealing with right triangles, but here we've got a triangle that's not a right triangle. So I'm going to do an example where I solve the triangle. Now when I say solve the triangle, what I mean is find A, B, C, alpha, beta, and gamma. And yes, I know gamma does not make a C sound, but it's the third letter of the Greek alphabet. So we're going to solve the triangle. With alpha equals 40 degrees, beta equals 60 degrees, and C equals 16. Okay, so solution. One thing to remember is that in any triangle in the plane, we have that alpha plus beta plus gamma equals 180 degrees, which means if I plug in alpha and beta, I have 40 degrees plus 60 degrees plus gamma equals 180 degrees. Well, basic mathematics, I subtract 100 degrees from both sides. That gives me that gamma equals 80 degrees. So it's just some straightforward arithmetic. So now, using the law of sines, and we say, well, I know what C is, so I'm going to use sine gamma over C and compare it to sine alpha over A. Now let's plug in the quantities that I know. Well, this is going to be sine of 80 degrees over 16 equals sine of 40 degrees over A. And, you know, I can multiply both sides by 16A. Why don't I just do this slowly? I'll do it step by step. Multiply both sides by 16A, and I get A times sine 80 degrees equals 16 times sine of 40 degrees. And then I'll divide both sides by sine of 80, and I get A equals 16 times sine of 40 degrees divided by sine of 80 degrees. Now I could compute this, but I'm going to go on ahead and leave it right there like that. If I compute it, that's fine, but since I'm not allowing you to use a calculator in this class, we're just going to leave it like this. Similarly, I can use the law of sines again and get that sine gamma over C equals sine beta over B. And I can use this equation to solve for B. I plug in what I know, and I have again sine of 80 degrees over 16 equals sine of, well, beta is 60 degrees over b. Do the same thing. Now I'll multiply by 16b instead of 16a. So I get b times sine of 80 degrees equals 16 times sine of 60 degrees. And in this case, I'm going to simplify sine of 60 just because I know what it is. You notice I didn't simplify anything here. But you know, what this gives me is b equals 16 times sine of 60 degrees over sine of 80 degrees. And this is an okay answer. Like this is a fine answer. But since I know what sine of 60 degrees is, I'm going to go on ahead and simplify it. I know it's square root of 3 over 2. So I'm going to get 8 square root of 3 over sine 80. I've got that over 2. And this is also a fine answer. You know, the 16 over 2 gives me the 8. So that's the basics of the law of sines. We can do a bunch of different things with this to solve different types of triangles. But the only real problem you might have is if you're not given information like this, like if you're given two side lengths and an angle, you might end up with the following situation where I've got, you know, this angle right here is given, and and I've got this side length, so it could either be, how does this work? It could either be like going all the way up here at this side length, or could be coming here. How does this work? This is not a very good picture, but occasionally you have problems like this, and what's going to happen is one or the other is going to work out. Sometimes you have problems like this where you just have two possible solutions. We're not going to worry too much about that. I think I did one of these in class, and I know this picture is messed up here, but we're going to try to not worry too much about that, at least for this final exam coming up. So I hope that made sense. Thanks so much.